Uh, Good evening, everyone. So I'll be presenting, this is part of my work for several years now, lately with my colleagues at the High Performance Computing Center at the University of Stuttgart, and with help from the DLR Institute of Network Energy Systems for the validation. A bit of context before, so that you understand part of the implementation choices. I started working on this project in 2012 as part of my master thesis. Hugo Capdevila, who was a consultant at the time, wanted to simulate plants with irregular terrain. And he was modeling some CPV trackers that were not rectangular, so that he couldn't do it. He was concerned also about mismatch because back then PVC5 didn't have this detailed mismatch calculation. And even back then, he wanted to go beyond hourly intervals. I left the project, joined in again in 2016. The idea then was to move towards a digital twin approach, and we would make a code so good that it could be used to monitor plants in real time. We had little money, so we had to work on some projects for plants in Europe and in Tokyo, and because of the low irradiance, then diffuse shading became a problem and part of the emphasis. In 2019, we organizes the High4PV project with HLRS and the DLR, and the focus shifts a little bit. First, for performance optimization, the code was very, very slow up to that point. Consolidation and validation using high quality scientific data from DLR, and data assimilation, because the emphasis of the High4PV project is short-term forecast. So it's less about bias and more about RMSE now. If you allow me, I will go a first pass very fast of the main 3 stages of the program, and then I will come back at the end. So first I will try to sell it to you, and then at the end I will do a second pass and tell you about the things that are missing and have to be published. If I have time, hopefully not. So I will not talk about every aspect, because a lot of it we just borrowed from PVLib and is not significantly different. With respect to irradiance calculation, maybe our core selling points are the decomposition, transposition, and shading algorithms. I will talk a bit about quality control later on. Direct shading is very similar to how PVC does it. You have a little bit more control because the grid of solar position, you can make it arbitrarily detailed. Maybe the difference is that we do not store shading factors, we store polygons. So for each table or tracker, you store the polygon, the vector of the light that is incident. That means that the electrical solver can go down to the sub-cell resolution if required to calculate the equivalent curve. You can use also fully anisotropic transposition. So that right now just means we take a continuous radius distribution model and then map it into an arbitrary tessellation of sky patches. So we calculate the radiance from each of these patches, and we calculate shading factors for each of these sky regions. This looks like an orthographic projection, but it's actually a custom projection that accounts also for the cosine response of the modules or the sensor that you're modeling. That means that the sides of these circular kind of shrunk to reflect that the light that comes from shallow angles is not all absorbed. All of this effort doesn't generate dramatic differences, but they can be important. So we did a parametric study, and you can tell that for some layouts, the lowest row accounts for modeling errors in the order of 1.5% RMSE. If you compare these very detailed anisotropic diffuse shading with isotropic plus circumsolar fraction model, which is what PVC does, for instance. As I mentioned, irregular terrain was one of the main points at the beginning. Right now, we can read digital elevation model rasters and triangulate it and combine it with cloud point data to calculate a single triangular irregular network. And we use that to calculate near horizon profiles for the center of every mount. So a mount can be a tracker, can be just a set of modules. You're free to define it however you want. For the detailed analysis, you need to specify your layout also very precisely. So you can tell here, this mount is defined. You see the modules, you see the cell blocks protected by diodes, and inside those, you even can define the polygonal outline of the cells if you want to get into how much of the cell is shaded. And the other one is the layout. You can specify the angles of every fixed table or of the axis for single axis, two axis, vertical axis trackers. More recently, we worked a lot with a dedicated class for meteorological data. The end goal is to have a presentation of the data that allows you to not throw any data away, so that we can avoid this problem we were talking about in the morning about where to fit the threshold for discarding data. The idea is that your class contains metadata for your sensors, including these last parameters that are a parametric model for uncertainty. So your uncertainty is not constant. It could be very much higher when the sun is lower, and include things like temperature, azimuth response. So the idea is this is stored inside, along with metadata for location, time step summarization, which is often missing, whether your interval started at the beginning, in the middle, or at the end, because if we're working with 5 minutes data, that's not straightforward. And each measurement has an associated 32-bit flags. You can define it whatever you want, and you can flag each of them independently without destroying the data. And also, it has an associated value for uncertainty. Some other features, typical automatic quality control methods. Some are more experimental. Detection of time offsets for short intervals becomes problematic. So we've developed these probabilistic metrics that at the end, they ask you as a user, like, it kind of looks like it's shifted. Are you sure? With 90% confidence, and then you can look into it. Some algorithms for gap filling. We're using now something called multivariable singular spectral analysis, which allows you, for instance, if you have 2 days without temperature measurements, you can infer it from the neighboring variables correlating with irradiance, and then have a coupled temperature irradiance gap filling over that period. Right now, we only use it by default for ancillary variables, temperature, pressure, relative humidity, etc. For the electrical calculation, the selling point is the circuit solver. We reproduce one-to-one the interconnection of the plant. So as part of the inputs, you specify a list of every module in the plant, where it is, and which string it is connected to, on which inverter, which MPPT. And we solved the circuit using a very basic series parallel curve addition. A big part of the work in the past 2 years, the HLRS was optimizing these algorithms. So using the minimum number of points to represent this one diode model, ensuring a given precision. And then ensuring that once you do the operation, the lines are still monotonic and descending, and simplifying them again to this given precision so that the number of points does not blow up. So this is now quite fast. You can solve a biggish system in the order of milliseconds now. There's still some bad stuff at the end. Sorry. And for data assimilation, this is my favorite part. Is my latest work is about making the most out of any data and any models that you have. The idea here, it's a Bayesian framework, and the idea is to combine forecasts with probabilistic separation models. So before having data, you already have an idea of where your data might be. So using those two, you get a step ahead probabilistic prediction. Your data from any sensor, tilted, direct, diffuse, horizontal, combined with a probabilistic transposition model and your sensor uncertainty model I talked about, gives you a likelihood in a state space. And those two combined give you ideally a better estimate or what your irradiance distribution is. And that's a data assimilated probabilistic estimate. So no matter how bad your measurements were, you don't have to throw them away. You just have to give them more uncertainty, and it will reflect on a higher uncertainty on your posterior. Then the posterior comes back and informs your step ahead prior for the next iteration. This is more how it looks like. In this case, the prior is a probabilistic separation model. We have a single sensor, 90 degrees south facing sensor with very high irradiance, and the combination of these two gives you the probability that Kn and Kd here is the direct and diffuse clearness index. So you don't have a single point, but it tells you your sky conditions might have this distribution with this and this probability. This is an application example for a PV plant we were modeling. That's the data using just out-of-the-box transposition models. And this is combining all of the sensors we have on site. So there's a horizontal planometer, an RSI, and a tilted sensor. And you can see that the effect is to shrink down and improve the estimates for a lot of the outliers. Overall, the RMSE goes down about 50% from 60 watts per kilowatt peak to about 40. In other cases, the improvement is not as good. So now I can go back to the limitations if I have time. Yeah, so the bad stuff. This is slow. It starts to resemble more and more a graphics engine programmed in MATLAB, which you can imagine is not a great choice. So eventually we'll have to port it using Vulkan or something like that. And it has a rather experimental ground shading algorithm, so shadows cast on the ground. We still do not manage the facial, but it's going in that direction, and we have to validate that part. Or anisotropic transposition and shading, we still have to find the sweet spot between complexity and performance. It seems that using 9 to 20 regions is more than enough, but we still have to play with measurement data and with different shading conditions to see where we fall. A very big limitation is that right now, this singular triangulated mesh does not cast sharp shadows. So these polygons that I talked about are the result of the shading algorithm, are generated only by neighboring trackers, because this was developed for standalone systems. If we want to use it for building integrated photovoltaics, then we will have to go into the shading algorithm and make each of these triangles also cast shadows on the modules. But we have not been wanting to change this because of the rewrite problem I already talked about. One limitation which most systems have, PVLib apparently not anymore, is that it assumes that the system is uniform, same tracker type, same module type, same inverter type. With respect to the meteorological data, since this is pretty new, it's still not implemented all the way to the end. The idea is that this uncertainty model is carried on, so it passes through the Bayesian recursive algorithm to calculate combined uncertainty from all the sensors and model, and then it's pushed forward through the electrical calculation, and at the end you have an uncertainty value for your production value. At this point, this cuts down after quality control, and all of this metadata is just thrown away, and the electrical calculation is just deterministic. I was going to talk about this. Performance is still an issue. Part of this is ported, the one diode model that we're using. The functions are already ported and optimized into C++. And so is the series parallel addition and the piecewise linear representation. But the interface between MATLAB and these optimized libraries is very slow. It has a lot of overhead. So we have to kind of bring the porting up. And we are expecting maybe 10 to 20x improvements on this side. And about this model, there's a lot of work to do. Probabilistic separation models and transposition models are not common, so they have to be developed and validated. And most importantly, right now, we are using these two variable state vector, just diffuse and direct. If we want to get the most out of it, we have to include at least albedo and a circumsolar component. Otherwise, we will not realize really the improvement in accuracy after the transposition model that we hope to see after this. Another issue is performance. Right now, this is called using a so-called gridded filter approach, which just literally means you test every point over a grid of values of your state space, and you see what the probability is at each point. But that's a lot of calculation, so we want to change to a particle filter approach, where it's represented more as a mixture model of analytic distributions, and then these are allowed to shift so that you can represent a multi-dimensional state space using only a handful of distributions. And that's it. All of the code is on GitHub. I've done my best to document it, but it's a lot of work, so please test it. If you get stuck, write me. I will be happy to try to get it working and help.